Previously, we had talked about the power series, c sub n times x minus a to the n power, that it would do one of three things. It would either, 1, converge, and that would be when the absolute value of x minus a was less than r, or if it were greater than r, it would diverge, and if it were equal to r, it would be inconclusive. For our first example, let's take a look at this series, x minus 2 to the n over 10 to the n. I can think about this as x minus 2 all over 10 to the nth power. Keep in mind, for a geometric series, the absolute value of r must be less than 1. So I have x minus 2 over 10. The absolute value of that is less than 1. So the absolute value of x minus 2 is less than 10. So comparing this to our statement up above here, that would tell us that our radius is 10 and we're centered at 2, which makes sense when we consider what our IOC is supposed to be. It's supposed to be negative 8 to 12. We are going to say that our series is absolutely convergent from negative 8 to 12. It is conditionally convergent, never, and therefore its IOC is negative 8 to 12. N times x plus 3 to the n all over 5 to the n. Because it's got an x in it, we're going to be using the ratio test for absolute convergence. The limit as n approaches infinity, and it's going to be the next term over the previous term. So throw your absolute values in there, write your next term, so make it n plus 1 times x plus 3 to the n plus 1 over 5 to the n plus 1, and then flip that fraction. So 5 to the n over n times x plus 3 to the n power. Let's simplify this carefully. Okay, the 5 to the n's cancel, leaving yourself with a 5, because remember, I'm going to write it here on the side, 5 to the n over 5 to the n plus 1 is the same as writing 5 to the n over 5 to the n times 5 to the first. So what else can we do? We can do the same kind of thing with the x plus 3's. We're going to cancel out all but one of them. So far I have a 5 on the bottom and x plus 3 on the top. And then we can get rid of the n plus 1 and the n completely, because as n goes to infinity, n plus 1, that plus 1 is too small to matter. So what we're going to have left here now is simply the absolute value of x plus 3 all over 5. Now remember, we're using the ratio test. What do we want to have happen here in order to be able to successfully use the ratio test? Well, the ratio test says that if the limit, and this is our L, right? If L is less than 1, then the series converges. So we're going to force x plus 3 over 5 in absolute values to be less than 1. That means x plus 3 is between 5 and negative 5. I can tell that my radius of convergence is 5, and I'm going to be centered around negative 3. Because this is the ratio test for absolute convergence, that means I know that my series is absolutely convergent on this interval. Now what else does the ratio test say? Our ratio test said that if L was less than 1, the series converged. Do you remember what the test said when L was greater than 1? It diverges. What happens when L is equal to 1? It was inconclusive. So I have no idea if the series converges at x equals negative 8 and at x equals to 2. So we're going to test x equals to negative 8. So by testing that, I mean I'm going to plug in to my original series x equals to negative 8. So I'm going to have n times negative 5 to the n, and then you have 5 to the n on the bottom. Well, let's clean this up a little bit. Now this is an alternating series because I have a negative 1 to the n power. I'm going to use the nth term test on this. The limit as n approaches infinity of n times negative 1 to the n power. This is going to not exist. Therefore, our series diverges at x equals negative 8. So now I'm going to test what happens at x equals to 2. So I'll have n times 5 to the n over 5 to the n. So what we have left is the series n. Can do the nth term test. Therefore, it diverges at x equals to 2. So as our final answer, we will say that our series is absolutely convergent on the interval negative 8 to 2. It is conditionally convergent, never, and therefore its IOC is negative 8 to 2. Let's try this one. X plus pi to the n over the square root of n. What I do see on here is that I have an x, and I don't know the value of the x, so I'm going to have to use the ratio test for absolute convergence. So now let's evaluate our limit. The square roots are going to cancel because as n goes to infinity, n plus 1 and n don't differ by much. I can cancel out n of these x plus pi's, leaving me with only one of them. So I have absolute value of x plus pi left over. If the absolute value of x plus pi is less than 1, then the series converges. X plus pi is between 1 and negative 1, so x is between 1 minus pi and negative 1 minus pi. And it is going to absolutely converge on that interval. What I don't know is what's happening at the endpoints. And that's going to be at x equals to 1 minus pi and at x equals to negative 1 minus pi. So when I plug in 1 minus pi, I get 1 minus pi plus pi to the n over the square root of n. The pi's cancel out. Positive 1 to the n might as well just be 1. And then we have the square root of n underneath this. What type of series is that? That is a p-series. With p equals to 1/2, which is less than 1, therefore the series diverges. So what this says is the series diverges at x equals to 1 minus pi. So now we look at the other endpoint. What happens when I plug in negative 1 minus pi? I get negative 1 minus pi plus pi to the n over square root of n. I have a negative 1 to the n over the square root of n. What kind of series is this? So I'm going to use the alternating series test. Well, what does our alternating series test say? Says that we have to identify our u sub n, which is 1 over square root of n, and we have those three conditions to satisfy. Are all of the terms greater than 0? Yes. Are all of the terms not getting any bigger? So if I plug in 1, I get 1 over the square root of 1, and then I get 1 over the square root of 2, and then I get 1 over the square root of 3. Yes. Now the denominators are getting bigger, so the fraction's getting smaller, so I know they are not getting bigger. And then the last part of it, does the limit of 1 over square root of n equal to 0? Yes, because the denominator is growing and the numerator is constant. So this tells me that our series converges, but is it conditional or absolute convergence? So when we throw absolute values over this, we have 1 over the square root of n. And look, we already did this one. This was done over here. And I know that this series diverges, so look at what we had done. We were checking for absolute convergence by putting absolute values over it, but it did not converge, it diverged, so this is what we call conditionally convergent. So the series is conditionally convergent at negative 1 minus pi. So we're going to take this and this and put those together. I'm going to write that over here on the side. We are absolutely convergent at negative 1 minus pi to 1 minus pi. We are conditionally convergent at the point negative 1 minus pi. So to tell me what the IOC is, you kind of put these together. Combine the absolute and conditional convergence. It's negative 1 minus pi. Notice the bracket now. It's a closed bracket and open at the right. So this is the difference between absolute, conditional, and then our IOC. Okay, so just kind of reviewing over what we had written up here, we had to do a number of things. So of course, whenever you see a problem that's like this, that has an x in it, and it is not geometric, it's going to be potentially one long problem for you to work on. Okay, so the first thing we had to do was check with the ratio test for absolute convergence. Then we find the IOC that we have so far for absolute convergence. You test the endpoints, and you have to test the endpoints, guys. Okay, nobody's going to say make sure you test the endpoints. You need to remember that the ratio test fails at the endpoints, so you must test the endpoints. So over here on the left-hand side, I plugged in one endpoint, and over here on the right-hand side, I plugged in a second endpoint. Each of those endpoints, when plugged in, creates a new problem that you have to deal with, a new series. I don't want to say problem, it's not a problem really, it's a new series. And the series on the left, we decided and figured out that it was divergent, so that was done. And then the series on the right, when we plugged in our endpoint, we found out that we got an alternating series. Alternating series do require a little bit more work because you have to check for absolute or conditional convergence. Try to remember that you can't ever have a conditionally convergent series if it was not alternating to begin with.